Welcome to Mining of Massive Datasets. I'm Anand Rajaraman, and today's topic is MapReduce. In the last few years, MapReduce has emerged as the leading paradigm for mining really massive datasets. But before we get into MapReduce proper, let's spend a few minutes trying to understand why we need MapReduce in the first place. Let's start with the basics. Now, we're all familiar with the basic computational model of CPU and memory, right? The algorithm runs on the CPU and accesses data that's in memory. Now, we may need to read the data in from disk into memory, but once the data is in memory, it fits in there fully, so you don't need to access disk again, and the algorithm just runs in the data that's on memory. Now, this is a familiar model that we use to implement all kinds of algorithms in machine learning and statistics and pretty much everything else. Right? Now, what happens if the data is so big that it can't all fit in memory at the same time? That's where data mining comes in. And classical data mining algorithms look at the disk in addition to looking at CPU and memory. So the data is on disk. You can only bring in a portion of the data into memory at a time, and you can process it in batches and write back partial results to disk. And this is the realm of classical data mining algorithms. But sometimes even this is not sufficient. Let's look at an example. So think about Google crawling and indexing the web, right? Let's say Google has crawled 10 billion web pages, and let's further say that the average size of a web page is 20 kilobytes. Now, these are representative numbers from real life. Now, if you take 10 billion web pages, each of 20 kilobytes, you have a total data set size of 200 terabytes. Now, when you have 200 terabytes, let's assume that we're using the classical computational model, classical data mining model, and all this data is stored on a single disk, and we have to read it in to be processed inside a CPU. Now, the fundamental limitation here is the bandwidth, the data bandwidth between the disk and the CPU. The data has to be read from the disk into the CPU, and the disk read bandwidth for most modern SATA disks, a representative number, is around 50 megabytes a second. So we can read data at 50 megabytes a second. How long does it take to read 200 terabytes at 50 megabytes a second? You can do some simple math, and the answer is 4 million seconds, which is more than 46 days. Remember, this is an awfully long time, and this is just the time to read the data into memory. To do something useful with the data, it's going to take even longer. Right? So clearly, this is unacceptable. You can't take 46 days just to read the data, so you need a better solution. Now, the obvious thing that you think of is that if you can split the data into chunks, and you can have multiple disks and CPUs, you stripe the data across multiple disks, and you can read it in and process it in parallel in multiple CPUs. That's going to cut down this time by a lot. For example, if you had 1,000 disks and CPUs, instead of 4 million seconds, and we work completely in parallel, instead of 4 million seconds, we could do the job in 4 million by 1,000, which is 4,000 seconds. And that's just about an hour, which is a very acceptable time, right? So this is the fundamental idea behind the idea of cluster computing, right? And this is the standard architecture that has emerged for cluster computing is something like this. You have racks consisting of commodity Linux nodes. You go with commodity Linux nodes because they are very cheap. And you can buy thousands and thousands of them and rack them up. You have many of these racks. Each rack has 16 to 64 of these commodity Linux nodes, and these nodes are connected by a switch. And the switch in a rack is typically a gigabit switch. So there's 1 gigabit per second bandwidth between any pair of nodes in a